So our next speaker is Debasmita Mukherjee from the Nilkamal School of Mathematics, and she's going to be giving a talk on mathematical analysis of a dynamical model of mild atherosclerosis. So I will hand it off to her, and thank you so much for being here.
Thank you, Rachel. Hello, everyone. Let me start the talk. So this one this is actually a mathematical modeling of atherosclerosis. So the outline of my talk will be, at first I'll give a brief introduction of atherosclerosis, and then I'll go to the next part, which is I will be giving a schematic representation of the disease formulation, and then I'll give a non-linear ordinary differential equation model. So here I will be explaining that how to do modeling for a disease, and then we will see few numerical simulation results and how to connect these results with their respective biological significance. That also we will be seeing at the end, and then I'll be concluding my talk. So now let us see what is there in the introduction. So atherosclerosis is basically a chronic inflammatory disease, and it occurs in the intima layer, which is the innermost layer of the artery, and it is a primary reason for several cardiovascular diseases, for example, heart attack and stroke. And nowadays, it is very much important to develop mathematical models to understand the intricacy of several disease dynamics. And aim of this work was to develop one model which can contain a good number of cellular species, and we can understand the disease in a more better way. Now, this is a structure of healthy artery. This is called lumen, where smooth blood flows. Yeah, I'll just make it full screen. So here, where blood flows smoothly, and there are three layers in the artery: intima, media, and adventitia. And these artery layers and the lumens are separated by layers of endothelium cells. Now the plaque formation occurs in this intima layer. So the next diagram, which I am going to show, that will be that entire plaque formation is occurring in this intima layer. Now the endothelium cells, which we have seen in the previous diagram, it is there is no lesion earlier, but like when if somebody is having more cholesterol laden foods or certain accidents, and for several other reason, for like smoking or something, lesion occurs on this endothelium layers. Now once the lesion is created, then this is the low density lipoprotein and high density lipoprotein. They are the cholesterol, so they come into the intima layer, and inside the intima, these LDL particle, they get oxidized by free radicals, and together they become oxidized LDL. And when oxidized LDL is present in the intima layer, then endothelium cells, they secrete vascular cell adhesion molecule 1, and they attract monocytes and T cells inside the intima. Now inside the intima, monocytes becomes macrophages, and macrophage absorb or phagocytose oxidized LDL, and that is how this necrotic core formed. And when this formation, or when the cellular interaction is going inside the intima, then smooth muscle cells from media, they migrate into the intima layer, and then they form a collagen rich matrix outside this necrotic core. And now this cycle continues for several years, and then once this necrotic core becomes very huge, and it creates huge stress on this endothelium wall, and then when endothelium wall cannot take this limit, it breaks down and it goes out in the lumen area, and this is actually in foamy in nature, and that's how the smooth blood flow, here it gets blocked. So it causes an hindrance in the smooth blood flow, and which may result in any thrombosis or any serious myocardial infarctions. Now, next, let us go ahead with the modeling part. So the entire biochemical process, I'm going to show here that how to model this one. So here on my first equation is, this is the concentration, rate of change of concentration of LDL particle. So dl dt is equal to sigma L. Sigma L is the constant. I'm assuming here that there is a constant LDL resource, and which we can modify in another model. So for this model, I have assumed that LDL resource is constant. Then I have here that LDL and radicals are interacting inside the intima. So that's why the LDL, that's why here I have a negative term, that LDL is interacting with radicals and they are getting oxidized. So that's why it is a negative term for the LDL concentration. And then we have residual of LDL, or the this is the degradation part of LDL, which is not taking part in this plaque forming process. Next equation is on the concentration of radical. So here also I'm assuming there is a constant resource of radical, and radical is also involved in this oxidization process. So the term is same, that radical and LDLs are interacting, and then we have residual of radical. Next equation is on the oxidized LDL. Now inside the intima, oxidized LDL was formed from the interaction of radical and LDL. So that's why the source term for oxidized LDL becomes this same term, which we have seen as a negative term in the previous last two equations. And now oxidized LDL is interacting with macrophages to form the necrotic core. So this is a biological term, and here also we use this 1 plus x, because here we want to there is a saturation constant here. So ingestion of oxidized LDL by macrophages is representing by this term. And next we have residual of oxidized LDL. Now in presence of oxidized LDL, we have seen that intima secretes chemoattractant. So chemoattractant source is directly proportional with the oxidized LDL concentration, and then we have residual of chemoattractant. Next is the monocytes. As many as oxidized LDL are the presence of oxidized LDL are actually allowing endothelium cells to secrete vascular cell adhesion molecule, and that is attracting monocyte. So that's why monocyte is also dependent on the oxidized LDL concentration, and this gamma is actually representing the threshold value. So with the gamma value, we can actually calculate the threshold limit of the wall shear stress of the endothelium wall. Now, this is differentiation of monocytes into macrophages, and this is death of monocytes. Now, for the macrophages, this part becomes the source term because macrophages are getting formed by there are like a lot of monocytes are getting together, and they are forming the macrophages inside the intima. And also macrophages involved in the ingestion process. So there is a negative term here. And here I have death of macrophages. Now I have equations for T cells and smooth muscle cell. So for T cell, it is proportional to chemoattractant concentration. And then we have death of T cells. For smooth muscle cells, it is also proportional to chemoattractant. And this term is the migration of smooth muscle cells from media to intima. And then here also we have death term for smooth muscle cells. Now I have here foam cells and collagen. The ingestion term, that macrophage is ingesting oxidized LDL. Here I have assumed that alpha amount is going for the necrotic core part, and beta amount is going for the outside part. So alpha plus beta together, it is equal to 1. So these are the fractional part it is depicting. And here I have death of foam cells, and for the collagen part, it is the smooth muscle cells which is migrating from media to intima. It has been also added here. And then I have here degradation of collagen. So there are 10 equations in my model, and this was the model. Now, first, as there are 10 equations, so there are a good number of parameters involved in the model, and we have chosen non-dimensionalized first. So we made the model non-dimensionalized, and this is how we have non-dimensionalized the model. Now, first of all, we have to, once the model is ready, we have to see the solutions of these model systems, if they are positive or not. So that has been proved, and then we have proved that all the solutions are uniformly bounded, and also we have done stability analysis around the positive equilibrium point. So it has been found that it is locally stable. Now, next, as this is a 10 equation model, so to do further numerical investigation, it is little bit difficult. So that's why we have used a reduction technique. We have used here quasi steady state approximation theory, and here I have assumed all other cellular species are in the steady state condition, and we have taken this model. So with monocyte, foam cells, and collagen, only these three equations are taken forward for further investigation. And here you can see that capital P, some new term is present. So this capital P already has oxidized LDL, and all other variables are also present in the model. So later on, we will see the equilibrium points or the results which we were expecting from the 10 equation model, and the result with this 3 equation model are similar in nature. So then we have performed stability analysis for this reduced model also. So we have find out that every solution of the reduced model are positive. Then all solution of the reduced system are uniformly bounded, and reduced system is locally asymptotically stable, and also it has been found out globally asymptotically stable around the positive equilibrium point under certain conditions. These are the model parameters which we have used. These are the numeric values. So some of the parameter values we got from literatures, and some of them we have assumed for the present study. Now, this is the time series plot. Here we can see that all the 10 cellular species are present in this diagram, but we cannot visualize this rest of the thing. So the this one is showing the monocyte, and foam cells is the blue curve, and the collagen is the red curve. So that's why I have considered only these 3 variables for in the reduced model. So this is the time series plot for rest of the concentration which were not visible in the previous diagram. Now the reduction method is numerically valid, that how we can tell. So using this plot, so here you can see that the color one is from the original model, and the black one is from the reduced model. So this diagram is for the for monocytes. This is the time series plot for monocyte, which is clearly visible that it is merging. And this is the time series plot for foam cells, and this is the time series plot for collagen. So here in all these diagrams, we can see the trajectories are coincident with the from the original model and the reduced model. Now this is the diagram for the local and global stability of the reduced model. This is monocytes, foam cells, and collagen. So here we can take multiple initial conditions, and with multiple initial condition, we will see that all the trajectories will converge here in the equilibrium point. So these are the equilibrium points over here. Now next is bifurcation diagram. So we have find out bifurcation with respect to the parameter A33, and all other parameters we have kept same as it was visible in the last table. So what does it suggest? So it suggests that increase of A33 will decrease the concentration of oxidized LDL, and consequently less amount of chemoattractant will be drawn. So let me just show you where was A33 in the model. So A33 was here in the original model. Yeah, so A33 was the degradation rate of oxidized LDL. Okay, so with respect to A33, we have find out a bifurcation. So it says that if A33 increases, then it will decrease the concentration of oxidized LDL, and hence it will secrete less amount of chemoattractant, and that is how it is connected, that relatively smaller amount of T cell also will be attracted, and it will break the autoimmunization process, and hence the plaque formation will accelerate. So that's why the bifurcation diagram has been obtained, and bifurcation shows it shows the transfer between stable nature to unstable nature for any dynamical system. Now next diagram is a bifurcation diagram with respect to A92. So it suggests that decrease in death rate of foam cells A92 leads to a large amount of active foam cells in the intima. So this is the death rate of foam cells. So with respect to that also, we have find out a bifurcation, and hence as death rate of foam cells decreases, then obviously plaque formation will accelerate. So hence it shows the bifurcation here. And next bifurcation we have find out with respect to A103, which is the degradation rate of collagen. So this is also suggests that decrease in degradation rate will lead to a large amount of collagen rich matrix, and hence plaque formation will accelerate here in the system. Now these are few phase portrait for the reduced I have taken here any three variables from the original model with 10 equations, and then we have seen that how the phase portraits are behaving. So you can see the stable nature of the phase portrait. So it also suggests the local stability of the original model. These are few two-dimensional projection from the original model. Here also randomly any two variables are chosen from the original model, and where the phase portraits are converging, that we have observed. Now next is concluding remarks. So as there are several important cellular species present in this model, this model can provide an inordinate insight for the in silico treatment and subsequent assistance in clinical investigation for this disease. And this model is actually find out stable, or it can be it has been proved globally stable also under certain conditions. So it can withstand a substantial change in the parameter values also. Now in the future scope, there are several other cellular components involved in atherosclerotic plaque formation. So for example, high density lipoprotein. So I have extended this work also with the involvement of high density lipoprotein already. Now I am working on developing models on including platelet derived growth factor, then matrix matrix metalloproteinase, then interferon gamma, and TIMP, interleukin 12. So all these components and how they are involved in the plaque formation, that also we can develop develop with some models, and we can do further investigations also. These are few references from my talk. Thank you.
Thank you so
So
much
now,
for that talk. Sorry. I was saying thank you so much for your talk. And then we do have time for questions. So if anyone has questions, please feel free to ask them now.
Hi, Deb. Thank you for your talk. It's a system I don't know enough about, so there was a lot there, but since I will have your slides, I can read it more carefully and understand it better. I think it's a very useful, if complicated, topic to be getting into in a way that we can understand it. Thank you.
yeah, sure. Thank you.
These medical systems are very complicated, and I think that's why we don't know enough about them. You're helping us get there.
Sure.
Does anyone have any last questions for Debasmita on her talk? Okay, then just
So,
to reiterate again, thank you.
Just 1 minute.
Yeah.
I am available. So like if anybody of you, if anyone is interested to learn it further, so you can just send me a mail. I'll just drop my mail in the chat box.
Thank you.
And we can
That
stay
was good.
connected. Yeah.
That will be excellent. Thank you again. It was a good talk.
Yeah.
Yes, thank you again for your talk. Thank you again for coming, and thank you so much, Debasmita, for your talk.
Thank you.